Ionization enthalpies. There is an increase in the ionization enthalpy along each series of the transition elements from left to right due to an increase in the nuclear charge which accompanies the filling in of the inner d orbitals. Table 4.2 gives the values of the first three ionization enthalpies of the first series of the transition elements. So these values show that successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of the increase in the second and third ionization enthalpies for the successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metals of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. So you have learned that when d block elements from ions, so d block elements form ions, ns electrons are lost before n-1 d electrons. So as we move along the period in 3D series, we see that the nuclear charge increases from scandium to zinc, but electrons are added to the orbitals of inner subshell, that is 3d orbitals. These 3d electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decrease less rapidly. Thus, ionization enthalpies increase only slightly along the 3D series. The W or more highly charged ions have Dn configuration with no 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases because one d electron does not shield another d electron from the influence of nuclear charge because d orbitals differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks for the formation of Mn2 positive and Fe3 positive respectively. In both cases, ions have d5 configuration. Similar break occurs at corresponding elements in the later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nuclear, repulsion between the electrons, and the exchange energy. So this is important. So three terms responsible for value of ionization enthalpy are attraction of each electron towards nuclear, the repulsion between the electrons, and the exchange energy. The exchange energy is responsible for the stabilization of energy state. Exchange energy is appropriately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponding to maximum possible extent of single occupation of orbitals and parallel spins, Bohn's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy of D6 configuration, Mn positive as D3, D5, 4s1 configuration, and configuration of chromium is positive is D5. Therefore, ionization enthalpy of manganese is lower than chromium positive. In the same way, Fe2 positive at D6 configuration, Mn2 positive 3D5 configuration. Hence, ionization enthalpy of Fe2 positive is lower than that of manganese 2 positive. In other words, we can say that the third ionization enthalpy of Fe is lower than that of manganese. The lowest common oxidation state of these metals is +2. To form the Mn2 positive ions from the gaseous atom, the sum of first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows usually high values for chromium and copper, where M positive ions have D5, D10 configuration respectively. The value for zinc is correspondingly low as the ionization causes the removal of one 4s electron, which results in the formation of stable D10 configuration. The trend in the third ionization enthalpy is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from D5 and D10 zinc 2 positive ions. In general, the third ionization enthalpies are quite high also. The high values for third ionization enthalpies of copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation state, this problem is very complex and not amenable to ready generalization.